Okay, hello. We continue the lesson. This is in the book they are called applications of the chain rule, but might be the more appropriate title is the title of related rates. Usually, I don't know, for some reason students find this hard. In principle, there might be hard questions, but I don't think it's very hard at this level. So let me start with an example, because I think this is easy. So I would say that let's consider a circle whose radius is increasing at the constant rate uh, 2 centimeters per minute. Okay, so consider a circle whose radius is increasing at the constant rate 2 centimeters per minute. What does it mean? It means that, roughly speaking, if you wait 1 minute, the radius has increased 2 centimeters in size from its previous value. So the question is that how fast is the area of the circle increases when the radius is, say, 10 centimeters. So it's a very simple and typical question. I will describe this in full details so that you understand what is going on, and then we go to solve harder problems, because this is something you need to practice to learn. Okay, consider a circle whose radius is increasing at the constant rate 2 centimeters per second. So it means, roughly speaking, if you wait 1 minute, if the previous radius was 4, if you wait 1 minute, the new radius is 6. Yes? Every minute it increases by 2. So now the phrase how fast is the area of the circle increases when the radius is 10 centimeters. Okay, so of course, implicitly speaking, it means that the radius is smaller than 10 right now. But when the radius reaches to 10 centimeters, you want to see how fast the area is changing. Okay, first of all, I want to ask your intuition. When you say how fast, what do we mean? Yes?
How much happens each instant?
No, there is a very clear meaning to how fast, yes?
What is the slope of the time that line to that point?
Yes, a better saying. When you say how fast is something is changing, you mean how fast over what? Because when you say how fast something is changing, it means something is changing with respect to something else. And you want to know how fast it is changing. So it is coming from physics. So when you say how fast, it means over. Yes, Rasmus?
Like with respect to time?
Time. That's the meaning of the phrase. So if you be careful, that's the same thing in math here. So when I say how fast is the area is changing, I am asking you, okay? If you have doubt, consider it as a convention, okay? But how fast means tell me how the area is changing with respect to time. I am using the word how fast. Okay, is that clear? Okay, But one thing that I want you to understand why this is a better name as this American book has written it. This is a university book, by the way. This you will start studying at KTH first. Okay? So consider a circle whose radius is increasing at a constant rate, 2 centimeters per second per minute. How fast is the area of the circle increases when the radius is 10? Of course, this is important to understand because the radius is changing over time. You expect that the area also changes over time. Okay? But the formula of the area of a circle, as you learned in mathematics, is a formula of the area that connects the area, to radius, not area to time. Is that understandable? That's the whole point. You see, I want you to understand this connection, because if you understand, more or less we are done. Let me call the quantity area A. Okay? This area, forget about this lesson. Area in geometry is a function of the radius. It depends on the radius. If you change the radius, the area of the circle changes. What does it mean? It means that A can be viewed as a function of radius. Okay? This is always. And how this connection is, if you remember, better. If not, you look at the formula sheet. So how area and radius are related in a circle? Area is pi r squared. So this you already know. Okay? But they are asking how fast the area is changing. So they want to know about the rate at which the area is changing over time. This is the meaning of the word phrase. Okay? But now, in this problem, they are telling you directly that the radius is increasing at the constant rate of 2 centimeters per minute. It means they are telling you that over time, radius is increasing. So it means that radius is also a function. But function of which variable now? Which? Time. So let me call it t for time. So A is a function of radius. In this setup, the radius is also a function of time. Is it fair to say that area is a function of time? A depends on R depends on time, so in principle A is also a function of time. Okay? But when I write this formula, I only see the dependence of A and R, not A and T. Okay? But the question is not dA over dr. This is not what they want, because this is not the phrase how fast. This is the rate at which area is changing. It's sensitive to a change of radius. This is not the meaning of how fast. Yes, is that clear? So if I want to write it like this, A is a function of R, but R itself is a function of T. Yes, so that is A after R. A after R, that's the composition of two functions, A and R. Okay? And now what I want to know how area is changing over time. So it means that I have to take the derivative of this. But be careful. This is why I'm saying that the prime notation is not a good notation. This is why Leibniz notation is superior here. Because when I say prime here, I could have asked you A prime, then you can take the function, take the R as the variable and differentiate. But let me just mention it explicitly to you. Here, by prime, I mean the derivative with respect to my variable t. Okay, but you already know how to do this. So what is happening? A, do you remember this chain rule? Yes? If A is playing the role of outer function, R is playing the role of the inner function, and T is playing the role of my variable. In that problem, what does prime mean? Prime means derivative with respect to my variable. Here, prime means the derivative with respect to my variable, but my variable here is t. Okay, so do you remember the formula? This is so famous that you have to remember, I would say. So what is the derivative? The derivative of the composition is the derivative of the outer function multiplied by the derivative of the inner function. But for the inner function, you don't have to be careful at all. But for the inner function, for the outer function, you should calculate it where? At the inner function. Anyway, that was the formula of the chain rule. I am just reproducing it with different letters which are more suitable for the problem in hand. Yes? Is that clear? Okay. Now, be careful. What I know what I want to find. It tells you that how fast is the area increasing when, not always, they are asking you about a particular moment in time. When the radius is 10 centimeters. Okay? So I don't want to answer the rate at which area is changing at all possible times. No, I am interested in at the rate in which A is changing when the radius becomes 10 centimeters. But do I know when that is in the problem? No. How should I know that? There is no information there. I don't know that what time is that. Okay? So let us say let T naught. By the way, this English I didn't know about. I usually pronounce it note. It was wrong. So it's N-A-G-T. I don't know why that is. But anyway, this is A. So I'm still not sure. Is it O-U? But anyway, this is in American. In British English, they say note. And in American, they say not. Anyway, so if you don't like any one of them, it is called T0. Okay? So let T0 be that moment for which the radius is 10 centimeters. If you ask me, do I know the value of this? I don't know. Okay? So in other words, can you tell me, what is R of T0? It is given in the problem. 10. Yes? 10 centimeters. Okay, now how fast is the area of the circle increase when the radius is 10? It means that I am interested in this quantity, but when T is T0. So it means that the question mark wants me to calculate this. This is the question mark. But I replace every appearance of T with 0. So what happens? Yes? This is what I want. But let us try to I need to answer 2 question marks. This one, we should be able to understand from reading the problem again. What is that?
2.
Yes? It is 2. 2 centimeters per minute. Why? Do I really need to know the exact value of T0? No. Why? Because the rate is constant. So it doesn't matter at which instant of time I want to calculate this. This rate at which R is changing over time is constant. So this one is what? 2 centimeters per minute. Okay. Do you remember I told you when I was teaching the chain rule? Do you remember what is the difference between this and this? This tells you that first you replace x with gx and then differentiate. That is exactly what we want to calculate. But what is the meaning here? It means that you first differentiate and then replace your variable with the inner function. Okay, so if I want to calculate a prime of r of t0, I have to differentiate my function a first. But what is the name of the variable here? What is that? It is just 2 pi r. So if I ask you to differentiate this, giving the role of your variable to r, this becomes a prime of r is 2 pi r. Okay? And then you have to replace r with what? R of t0. Yes? So then it becomes equal to 2 pi r t0 multiplied by r prime t0 if you want to. I will teach it to do it faster, but I want you to understand what's going on. Okay. Do I have these numbers? Yes, this one is 2, this one is 10. I am done. So this becomes 2 pi times 10 times 2. What is the answer? It's 40 pi, but of course you have to write the units. What are the units? No. The length is measured in centimeter. The time is measured in minutes. And that is the rate at which the area is changing over time. So it should be minutes. What should I write above? It's an area, so it's centimeters squared. That's it. That's the answer. 40 pi centimeters squared per minute. Okay? But the way I do it, as everyone does it, is just do it faster using the Leibniz notation. So let me write it here. When this problem becomes relevant, if you have a function that depends on a quantity, if you have a quantity which depends on a quantity, and that quantity in its own right depends on another quantity. Whenever this happens, this is what is this topic. And you somehow want to find the rate at which this quantity is changing with respect to the last quantity. Okay? So whenever you have one quantity which depends on another quantity, and that quantity also depends on another quantity, but your goal is to know what is the rate at which the first quantity is changing with respect to a change of the last quantity. Whenever this is wanted in your problem, you need to remember this trick. And that's not a trick, by the way, that's a chain rule. Okay, but I write it in this way. So when I read that problem, I try to analyze the problem by drawing that diagram. And I see, when I read the problem at the very end, how fast is the area increases or changes with respect to time, because how fast means with respect to time. This tells me that I want the derivative of A, but not with respect to R, with respect to T. This is wanted. And then this tells you that you take the derivative of A with respect to the middle variable. So I am using the Leibniz notation. dA with respect to time is dA with respect to R, but multiplied by the derivative of R with respect to time. And memorizing it is extremely simple because you can pretend as if they are fractions. Yes? So memorizing it is extremely simple. So the derivative of the first quantity with respect to the last quantity is equal to the derivative of the first quantity with respect to the intermediate quantity multiplied by the derivative of the intermediate quantity with respect to the last quantity. Yes?
And does this, if you have like an arbitrary numbers of...
Yeah, this follows. Yes, it follows. Yes, and it is very easy to remember because we can pretend that they are just normal fractions if you don't need to press your memory so hard. Yes? Is that clear? So now if I want to solve that problem, what I will do, this is the proper way of doing it for all details. But what I do, I will write this formula. So first of all, There is only one formula that I know for area of the circle. So I write the formula. What does this mean? It means that I immediately connected these two quantities. And this tells me that the question mark is how fast. How fast means the rate at which a quantity changes over time. This is implicit in the word how fast. Okay, so this is wanted. But then this means what? This can be written according to this rule. Yes? And then I continue. If I ask you calculate this, it is an extremely simple task to do, yes? Because what does this symbol means in Leibniz notation? It means take the derivative of the quantity area when R is your variable. Okay, so I have this formula in front of me. I take the derivative of this one as if R is my variable. It is like that px squared. How do you differentiate that? So you just write what? dA dr is what? 2 pi r. Okay? If I ask you r prime, what is r prime here? Because my variable is r, so I prime, r plays the role of x. So r prime is 1 here. So that's it. The derivative of a with respect to r. And I put it here. So the solution becomes very simple. You draw a diagram like this in your head or whatever. You just write the formula. And then you know the question mark is this. And then you have to replace things for these two quantities. dA dr is extremely simple because you have a simple function in front. You take the derivative of that with respect to the same quantity that you see in the formula. Everyone agrees it is 2 pi r. And then you multiply it by what? Exactly dr dt. Now you want to answer the question mark. Not this is true for every moment of time. But we are not interested in every moment of time. We are interested only in that particular moment for which the radius is 10 centimeters. Yes? Okay? So what I do, I continue. It becomes 2 pi. What is r in this case? 10 centimeters. Because I told you, this is valid for all moments in time. But I am interested for that case that r has reached to 10 centimeters. And then what is dr dt? dr dt is the rate at which the radius is changing. But because of the phrase constant, it is independent from when I am looking at it. The rate at which the radius is changing over time is always constant value 2. So I put 2 there, and then I write the units. So this is the solution, which of course becomes the same answer. But I did it in that way because I want you to see that is exactly the chain rule written in a more efficient way so that we can do it to do things faster. Is that clear? Yes? Okay, let us solve some problems. So let me write one example from me and then I will go to this better problem. So there's also one very nice problem from national exam in your book. Yes, we will solve that one as well. So, example. So let me write this. Consider a spherical balloon, yes? Spherical balloon. Air is being pumped into the balloon at the constant rate of say, for example, 0.02 cubic meters. So this is too much, so let me make it smaller. 0.002 cubic meters per a minute. Air is being, I assume that it is always remain spherical. Air is being pumped into the balloon at the constant rate of this cubic meters per minute. How fast is the radius increasing when the volume of the balloon is, so let me write it in a way, I don't know. So let us write pi over 5 cubic meters. I don't know if it is reasonable or it will burst before that. Okay, you don't think about practical issues. If you don't like it, make it divided by, 5 is good. Okay. So how fast is the radius increasing when the volume of the balloon is this? It's a little bit harder question than the previous one, but I hope that it's simple enough to solve. Okay, so let me start from scratch. So I will not explain it in this long way. I want to use it like this. Okay, so how should we analyze the problem? So how many quantities are involved? We have the volume and time and what? The radius. Okay, so the first thing comes to mind is that the quantities that I have is V for volume, R for radius, T for time. So is it plausible to say V depends on R in a more proper terminology? V is a function of R, and in this problem R is a function of time. Yes, because when I am pumping air into my balloon, the volume is changing, so it will cause, of course, the radius is also changing. I will talk about this. Might be you think the problem should be arranged the other way around. Okay, I will talk about that one as well. Okay, but this is at least one plausible idea. V depends on R, R depends on T. Then immediately I can talk about how fast V is changing. How fast means the derivative of this quantity with respect to T. Okay? So according to the chain rule, this can be written as derivative of V with respect to the intermediate variable R, but you have to multiply by the derivative of the intermediate variable by the last one. Yes? Okay. So for this one, I do not have any formula. For this one, I do not have any formula, but for this one I have. Because if you see the formula sheet, there is a relation between V and R. So you read it or you have it in your memory. The volume of a sphere is 4/3 of pi times R cubed. This one is very easy. What is the meaning of this one? It tells you, take the derivative, differentiate this function as if R is your variable. Okay, so what is the answer? 4 pi R squared. Because 3 goes down, 3 cancel that 3, so it becomes 4 pi r squared. I put it back here. That is the area, by the way, of the sphere. So this dv dt is equal to, instead of this one, I put 4 pi r squared and dr dt. This is what you can write only. And then you have to go back to your problem to see, are these quantities given to you? Which one is wanted? Which one is given? Any questions about writing this? Okay, let us read the problem. Consider a spherical balloon. Air is being pumped into the balloon at the constant rate of this. Which quantity is given? Cubic meter per minute. Volume, time. So which one is that? So dv dt is equal to what? 0.002 cubic meter per minute. And does this depend on time? In general, it might depend on time, but because of the adjective constant, it means this rate is constant, and this is always this number. So I do not have any problems with that number. Okay, what is wanted? How fast is the radius increasing? So what the question mark is? How fast the radius is increasing? This is my question mark. Okay, I have this one, and I don't fight with this because that's my question mark. But in order to answer the question mark, I need to know this, which I know, but I also need to know another quantity, which is r. Yes? But r is not given to me directly in the problem. What is given to me? How fast is the radius increasing when the volume is this number? But that's also a minor thing, because if the volume is given, you can yourself find the quantity r. Okay, so what you do before solving the problem, you have to go and use this formula to find the suitable r for that particular moment in time. So I go and replace v with this quantity. Pi over 5 is equal to 4 over 3 pi r cubed. Agree? And then I want to find r. So pi and pi are gone. So this becomes 3 over 20. So r cubed is 3 over 20. So what r is? R is the cubic root. It is in centimeter. No, it is in meters. Now everything is ready. Go back here. Instead of dv dt, you can put that constant number. And then on the right hand side, you have 4 pi. R is this quantity. You raise it to power 2. So it becomes 9 over 400 to the power of 1/3. And dr dt is what you want. That's it. These are just fancy numbers. Then you calculate, you find your question mark. So dr dt is equal to 2 over 1000. Yes, which is 1 over 500. I prefer to write it in that way. So it becomes 400 over 9 to the power of 1/3. And then this goes down, it becomes 1 over 2000 pi. Yes? It's 1 over 500. 4 pi goes down. So that's correct. That's also correct. Whatever this fancy number is, what you have to write the units. R is radius. Length is being measured in meters. How I know that? Because volume is in cubic meter. So this becomes meter per. Time is measured in minutes. This was a slightly harder problem.
Yeah, yeah.
Is that understandable? One thing comes to mind is that am I forced to keep the order? Because at the end of the day, if V is a function of R is also a function of V. Might be in your head it is more natural to write in this problem RVT. Okay? Yes?
So, I mean, I guess if you can like construct a
Because you know why RVT is more natural in this problem? Because the question mark is not DR, is not DVDT. DVTT is given, the question mark is DRDT. Okay? So if you think it is natural to write RVT, I want to describe, yes, it is possible, but you see what is the obstacle in front of you, okay? For the people who want to understand deeper, let us solve the same problem with the arrangement RVT. Okay, so, and then I want you to do a favor for me and then help me to write it down. So, I view the same problem, but with this arrangement. Okay? So what is wanted in the problem? How fast the radius is changing. So it means that you are interested in the rate at which R is changing with respect to time. This time you have to write dr with respect to v and then multiply it by dv dt. This is also possible. And this is probably more natural, because the question is asking about how fast the radius is changing. So the question mark is really this one. And the problem is that I have it because dv dt is given to me. Okay? I don't know. Might be this is, by the way, might be this is simpler. But the reason that I avoided that is what can you see that? Yes?
to make like an inverse.
Yes. So here, that is because of algebra I skipped. Because here you need to write R as a function of V. Or you need to know implicit differentiation. But that is not part of our lesson. So dr dv is wanted. So this means that I have to express R as a function of V, not V as a function of R. But the usual formula is this one, which expresses V as a function of R. But if you insist, you go to the formula sheet, then you find R as a function of V. How should I write that? So I multiply by 3, divide by 4 pi, and then take the cubic root, yes? Okay, in that case, what I'm supposed to do, I can simplify this. R becomes the third root of 3 over 4 pi, and then the third root of v. And if you don't mind, let me write v to the power of 1/3. Yes? If you insist to do it in this arrangement, it is possible, but you have to suffer a little bit in differentiation. Okay? Because now, if I ask you what is dr dv, this is a constant. I don't touch it. But this 1/3 goes down, and v to the power of 1/3 minus 1, which becomes minus 2/3. And then put this there. Okay? So now the question mark, at least the benefit is that the question mark is exactly given to me now. dr dv is that guy, so it is 1/3, the third root of 3 over 4 pi, and then v to the power of minus 2/3. I bring it down, okay, and then make it positive, and I put the third root of v here to the power of 2. These are just minor things. Okay, so let me make it clear that this is a v. This is this quantity multiplied by dv dt. To be honest, that is not that bad. I avoided that because I didn't like this differentiation. But now everything is ready-made, yes? What should I put here? Let us read the question. Air is being pumped into the balloon at the constant rate of this. So this one I know is this number. And the good point again is that how fast is the radius increasing when the volume is this? So I also know the volume, I just need to put the volume there. I don't need to calculate any R. And then, because I am lazy, do it yourself and convince yourself that this becomes the same number. Okay? But that is not that bad. So the reason, the book hasn't discussed about this issue, but the reason I take it in that form is because the formula that I have in the formula sheet expresses V in R, and because it is a polynomial function, differentiation is simple. If I want to make it like this, the differentiation involves rational powers, makes it a little bit harder. But that is it. And this is suited actually to this problem, because you remember when I wanted to solve the problem using this, then I realized, oh, I don't have R. So I had to go back and calculate R. But that is not any obstacle anymore, because what I need is V, and V is given to me directly. That's up to you, which one you choose. But I will always use that one. I don't know. I have learned doing it in that way. It's faster for me. Okay? Is that clear? Okay. So this is the essence of the lesson. Let us solve some problems. One problem is interesting here. Let us write this down and solve it together. And there is also a very nice problem in your book, but it is from the national exam. The translation is hard for me, but I realize what's going on. So I will try to solve it together. Okay. But I will write one problem here, wait for you, okay? That is exactly the problem that I want to choose from this Calculus, a Complete Course by Robert Adams, okay? Okay, so the problem, I just write it's exactly the same thing. If I can lift that book and simultaneously read and write. Yes, because I also need my glasses, but we'll forget about that, hopefully. So this example is a good one. An aircraft is flying horizontally. An aircraft is flying horizontally at a speed of 600 kilometers per hour. Okay, how fast is the distance between the aircraft and a radio beacon, how fast is the distance between the aircraft and a radio beacon increasing 1 minute after the aircraft passes 5 kilometers directly above the beacon. 5 kilometers, of course, passes 5 kilometers directly above the beacon. Okay, I don't know, because I see the picture here, so I cannot judge if I could understand what this would mean. But understand. By looking at the picture, I understand. So let me also describe that because that's minority. I want to make sure that you understand the problem correctly and then start solving it. So an aircraft is flying horizontally at this speed. How fast is the distance between the aircraft and a radio beacon increasing 1 minute after the aircraft passes 5 kilometers directly above the beacon? Is the text clear?
So like 5 minutes up in the air from.
Yeah, I mean, you need. This is what is written. But anyway, I see the picture here. This is what they mean. This is the ground level. This is the ground level. And then let us say that you have your radio beacon here. Okay, beacon. And then an aircraft is going horizontally. How fast is the distance between the aircraft and the radio beacon increasing 1 minute after the aircraft passes 5 kilometers directly above this one? So it means that let us go 5 kilometers directly above. So this is 5 kilometers. Okay, so the aircraft is coming in this horizontal line. After it reaches to this point, 1 minute later, the aircraft is somewhere here. I don't know. So this is your aircraft, okay? But 1 minute after this, you want to see how fast the distance between aircraft and the beacon is changing over time. Okay? But the question is hopefully clear, yes? This picture is now make it clear. So the aircraft passed this point at some point. After that, 1 minute later, the aircraft is at some point. And of course, the distance between the aircraft and the beacon is continuously increasing. For example, the distance was this much. Now the distance is longer. If the aircraft is here, the distance is longer. Now I want to see how fast that distance is changing. So I want to wait for you. Because if you can solve this problem, actually you understood everything, yes? The rate at which this quantity is changed is constant.
Yes.
Because the airplane speed is constant. But this rate is not constant, as you will see. Yes? So for example, if the aircraft is here, this is this distance. If the aircraft is here, the distance is a little bit longer. But I hope that you agree with me, if you have a little bit of intuition, what do you think will happen? Do you think that the distance between the beacon and the airplane is constant? No. Do you think that this rate is going up or down? It seems to go higher, yes?
It should be exponential.
Yes. I don't know, we can also calculate. But anyway, I want you to think before I intervene. Okay, what happened? Yes? Let me try to solve the problem. An aircraft is flying horizontally at the speed of this. And how fast is the distance between the aircraft and a radio beacon and the radio beacon? Yeah? No. A radio beacon increasing 1 minute after that. Okay, so what are you interested in? So you need to explore the quantities. In the previous problems, the quantities were more or less easy to detect. So what are you interested in? You are interested in this distance. Yes? How this distance is changing. So let us call it D. Okay? And then when you say how fast is, oh, by the way, D is not a good thing because it will be confused with D for derivative. So let me call it S. Okay, so what are we interested in? We are interested somehow to calculate how fast this distance is changing. It means that we are interested to calculate the derivative of that quantity with respect to time. Okay. But I have to write it in a way that I can differentiate it. S is just the distance. How can I differentiate it? First, you need to set up a function yourself. Because that function in the previous problems were clear. I just read it from the formula sheet. Because that was the volume of the sphere or whatever. But this quantity should be written in what I have information about. So how can I write something which is useful in this context? Because I need to, if I want to differentiate s, I have to have the function s as a function of time, finally. Okay? So what should I do?
Just define s, or like write it.
Write it what?
So the formula for the distance would be, well, I guess the first thing I would do would like just create a temporary function that is like I don't know, x, whatever, of t.
Yes.
That is how far we
Exactly. So let us call this one x. Yes? And then what should I do? I need to connect these quantities. But the connection is extremely simple because that's a right angle triangle. So I connect them. So what should I write? I write s squared is equal to what? 5 to the x squared plus 5 to the power of 2. So this means s squared is x squared plus 25. I am looking for s. S becomes the square root of x squared plus 25. Yes? And I don't need to put plus and minus sign. Why? Because s is the distance, so it cannot be negative. Otherwise, you have to put plus and minus. Okay, but what the question is, now you understand what is happening. Is it reasonable to assume that s is a function of x? It is clear. S changes when x changes. But is it reasonable to assume that x itself is a function of time? Yes, because x is the distance from the aircraft to this. And when time passes, this distance changes. So s is a function of x is a function of t. What is wanted in the problem? The rate at which s is changing with respect to time. So we use the same trick. What is the trick? ds dt is equal to ds dx times dx dt. Am I right? Okay, but this is a little bit harder problem because for ds dx, if you don't mind, let me calculate it here. What do I need for ds dx? What do I need for that? If I ask you to differentiate this when x is variable, we practice about these problems a lot. So that is the chain rule itself. Yes? So I take this u in my head. Do you remember? So, and I go to the formula sheet. Square root of x is 1 over 2 square root of x. I told you that when you have a square root of u, you will follow the same rule. The only thing that you have to remember is to multiply by u prime. Okay? So I will do the same thing. So ds dx is equal to 1 over 2 square root of x squared plus 25. But it is not finished. I have to multiply by this. But then copy paste this one. This becomes 2x. 2 and 2 are cancelled. X is left. This is ds dx. Do you agree? Okay, I put it back in my formula. ds dt, which is wanted, is equal to ds dx, which is this quantity, multiplied by dx dt. This is your fundamental relation. And now I have to put the numbers in at that moment of time in which the problem is interested. Yes? Okay, so this formula is completely generic. It works for every x and for every instant of time. But I'm not interested in all instants of time. I am interested at that moment, which is 1 minute after this happens. Okay? So, what do I need to calculate? I need to know my x. I need to know dx dt. But I think you can immediately tell me by reading the problem again, what is dx dt? Yes? 600, yes? dx dt is how fast x is changing over time. How fast x is changing over time is the speed of my airplane, which is 600 kilometers per hour. So this becomes 600 kilometers per hour. But can you tell me what x is? Yes, because x, I am looking at that moment, which is 1 minute after the aircraft passed this point. The speed of the aircraft is 600 kilometers. Yes, 600 kilometers per hour multiplied by the time. The time is 1 minute, which is 1/60 hours. You have to be consistent in your units. And then what happens? It becomes 10 kilometers. And then I put this back. So the question mark becomes, instead of x I put 10, square root of 10 to power 2 plus 25, multiplied by 600 kilometers. And that is your answer. So let us calculate this a little bit. So this becomes 6,000 divided by 125. Am I right? Yes. So this becomes 6,000. If I want to simplify this a little bit, this becomes 5 square root of 5. So it becomes 1. This is exact value. What should I write the units? Can you tell me? You have to write the units. What should I write? Yes, because this is the rate at which S is changing over time. S is a distance. Distance is being measured in kilometers, T in hours. So this becomes what? Kilometers per hour. This is the final answer. And that is exactly the answer given in the book as well. Is that clear? But let me teach you to do it in a different way. Okay? A little bit faster. Not because of this idea. Because I don't need to even take a square root sign. Okay? Let me tell you this. This is implicit differentiation, but it is not hard. So if I want to solve this problem myself, I will not continue exactly like this. I will come up to here, but then I start differentiation. Okay? How? I would say that s squared is x squared plus 25. Okay? When I want to differentiate, I differentiate with respect to time. Okay? And this is plausible because s is a function of time. X is also a function of time. So when I differentiate s, it becomes 2s as usual, but I have to multiply by s prime. But prime here means with respect to time. Yes? And then I do the same thing here. So it becomes 2x, but x prime. X prime is usually 1 because I am taking the derivative with respect to x. But here I am taking the derivative with respect to time. So it becomes dx dt. And this is 0. And then I can simplify 2's. It is better here. Okay? What is wanted? What is wanted? Of course, this is, you see, there is not a big difference because then it becomes x over s dx dt. Yes? But that is, if of course, if I ask you what s is, then you have to put that in. Anyway, but sometimes it is easier to differentiate implicitly. Sometimes because sometimes only derivative rule is needed. So in those cases, this is simpler than writing it that way.
Wait, what did we do when did we say that s squared is equal to s times ds over dt, or?
Yeah. So I'm not saying that that gives you exactly the same answer, but with a slightly different logic. Okay. So you take the derivative with respect to time, so it becomes 2s, but the derivative of s with respect to time, this becomes 2x, the derivative of x with respect to t, then I simplify 2. Because I want to know ds dt, I isolate it by dividing by s, and I got this result. But of course, this result is exactly identical to this result, yes? Because dx dt is exactly the same thing, and this is x divided by s. Yes? Okay, so that was also a good problem. Any questions? Okay,
Den har också konventionen.
But I think one of the hard questions is given in your own book. Okay, and that is a national exam book. So let me try to bring, of course, I don't know exact translations, but I understand what is meaning here. So this is a national exam 1996. Okay, so apparently those days you were more serious in Sweden, yes, than here. So because that question is a little bit harder than usual. So you have to have a good understanding of what's going on. I don't understand the translation exactly, but as far as I'm concerned is that there is a candle there in a spherical volume shape, and then it is burning. Yes, so it means that the volume is shrinking. And then there are some information given to you. So the original volume is 3 centimeters, cubic centimeters, and T time is measured based on month. And then after 1 month of that this candle is burning, the volume reaches to 2 centimeters, cubic centimeters. Okay? But one thing that is a little bit unusual to say is that the rate at which the volume is changing is proportional to the area of the sphere. Okay? So, as far as I understand the story, let me repeat it. So you have a candle or whatever that is, it's like a spherical shape. Okay, and you start burning it and the volume shrinks. So the original volume is 3 cubic centimeters, and after 1 month, the volume reaches to 2 cubic centimeters. But one thing that is very interesting to see is that it is given the rate at which volume changes per unit of time is proportional to the candle's area. So here, candle is just a sphere for me. Okay? You need to be able to interpret this phrase and then solve 2 problems. Part 1, show that the rate at which the radius is changing over time is a constant, which they call it K in this problem. Okay? First of all, based on what they told you that the volume, the rate at which the volume is changing is proportional to the area, you have to convince yourself that the rate at which the radius changes is a constant. And then calculate what is the volume of this candle if it continues burning for 4 months. It's a very good question. To be honest, I didn't expect that they will give you questions like this in the national exam. Okay, so let us think about it. Is the problem clear? So I have a sphere. The sphere is shrinking. Okay, so the sphere is shrinking. And the initial volume is given. The volume after 1 month is also given. On top of that, they have given you an extra piece of information. I don't know how they manufactured this candle anyway, but this candle is burning in a way that the rate at which the volume is shrinking is proportional, I will add this, instantaneous volume of this, area of the sphere. Based on these pieces of information, you need to prove that the rate at which the radius is, of course, shrinking in this case, is a constant. And then based on what you proved in part A, you are supposed to calculate the volume of this candle or this sphere after 4 months. So old days, I don't think we have any candle that lasts for 4 months. So at least it shows that the goods produced before actually was lasting longer. These days they just want to destroy it and buy a new one, yes? That was a different policy back then. How many years is that? 27 years ago. Okay?
So by proportion, so it means that the...
No, you need to interpret everything yourself because it's a very nice problem, okay? The phrasing might be complicated. The first one is extremely simple.
to show
Yeah, just write and then it is finished. What is the meaning of being proportional? When I say 2 quantities are proportional. For example, if I say quantity A is proportional, and then you know that this is something like alpha. This is the symbol of proportionality. I forgot the later code for it, but I think it's proportional, it's slash proportional or something. When I say two quantities are proportional, what do I mean? No, mathematically it means what? It would be a shame if you don't say what does it mean. Yes. You're the third technique. So what is the meaning of two quantities proportional? It means that if you scale one of them with, say, a factor of 3, the other one will also be rescaled by a factor of 3. If you multiply it by 5, the other one also multiplies by 5. Okay, what is another simpler way, parsimonious way of saying this? Okay? A is proportional to B if and only if what? There exists a K constant such that one of them is K times the other one. That is the meaning of two quantities are proportional. It means that there exists a constant so that one of them is K times of the other one. That is the meaning of two quantities being proportional. Okay? And now if you go back and read the question again, the rate at which the volume is changing per time, over time, is proportional to the candle's area. So what does it mean? What are the quantities involved in this problem? What are the quantities? So what are the quantities? The rate at which the volume is changing over time, means dV dt, is proportional to the area. That is what they are saying in words. Yes? But what is the meaning of this? It means there exists a constant K, constant, so that what happens? dV dt is equal to K times A. So by reading that Swedish or English sentence, you should immediately translate it into language of mathematics like this. Is that understandable or not? And then probably this K that appears here is the same K is probably they're talking about. Because you just want to show that the dr dt is a constant. So is that clear now? So how should I continue? Today we learned about this. Yes? dV dt is what? Is dV dr times dr dt. Yes or no? Okay, but here they are using little r for the radius. Let me also stick to the same notation. Okay, so dV dr, what was V? V was 4/3 of pi r cubed. So dV dr is what? This is 4 pi r squared. Sorry, 4 pi r squared. So instead of this one, I put 4 pi r squared is equal to, times dr dt is equal to K. And then if you look at the formula sheet, the area of the sphere is exactly 4 pi r squared. And then 4 pi r squared and 4 pi r squared are gone, so dr dt is K. So that is just the solution to the first part. So you see it was very simple if you just write it down. Yes? But the second one is a little bit more challenging. I don't want to solve it for you now. Next time I will start this all over again and then we solve it together. But I think if you can solve this problem and the one that I mentioned about the aircraft, that is enough. Of course, these problems could be sometimes very hard, but that's a different story. You don't need to know those things if you don't like to. Any questions?
Is it a coincidence that the derivative Oh, but
I saw one of these YouTube channels. I forgot the name. 3 browns, 1 blue, or something. Actually, he said something about how to visualize this. You can check that video out yourself. Yeah. Any questions? No?
Bubba, can
Yes?
you link that video you were talking about?
If I can find it, yes. Otherwise, you need to find it yourself. Okay. Have a nice weekend. Goodbye.
thank you.